Okay, so the pretty stuff in the atmosphere. Rainbows, we'll talk about rainbows. Okay, why rainbows occur. But kind of at the crux of why we get things like rainbows is something we've already talked about. The idea that energy can interact with matter. Okay, in this case, light can interact with particles in the atmosphere. They're either going to be liquid water droplets to give us rainbows, or ice crystals to give us halos and sundogs. Okay, but we basically have light interacting with matter. So when light interacts with matter, I know last time we said that actually that energy can be absorbed, energy can be transmitted, or energy can be redirected. Okay, we kind of said that before. We're going to focus on the two blanks that you filled in, reflection and refraction. Reflection and refraction. And you're already very familiar with reflection. Okay, these other two things, diffraction and interference, we won't really touch on much, but they also give you, diffraction, by the way, is like if you take a CD, okay, and you take the title side, you look at the back of your CD, and you kind of see these colors, okay, that actually is diffraction because there's like little grooves in your CD that is making light, breaking light out into its different colors. That's diffraction. So reflection, you're already very familiar with a mirror, the concept of a mirror. You look at your reflection in a mirror. Okay. So there's this thing called the law of reflection. And the cool thing about a mirror is when you look in a mirror, you know where your image is going to be. There's no like guessing. Okay. And that's kind of like what the law of reflection says. It basically says whatever angle you hit the mirror with is going to be the angle that it reflects at. The angle that you hit it with is called the angle of incidence. Okay, and the angle that it goes away at is called the angle of reflection. And when they say the angles are equal, they've kind of marked arc A and arc B here. Okay, this angle right here is equal to this angle right here. Yeah, and if you take physics, they'll talk a lot more about kind of how light, this law of reflection. But there's something what we call the normal, which is perpendicular to the mirror. But if you just know that the angles are equal, the angle of incidence is equal to the angle of reflection, that's great. So reflection, basically the way light interacts with this matter is it's kicked back. So this is also reflection, okay? But this is reflection when your surface is not smooth. So it's more of a kind of a random reflection. So instead of having a smooth mirror, an example would be like if you take a piece of aluminum foil and instead of being nice and flat, you crumple it up. This is kind of what you have. So again, you have reflective surfaces, but it's kind of more random. And the next slide actually is a picture of, or a photograph of a phenomenon that's created by this sort of kind of rough surface. So in this case, the rough surface reflection is being created by basically the water is not smooth, but the water is reflective. Okay, so instead of seeing the disk of the sun, you kind of see the shaft of the sun, kind of. It's all about reflection. Reflection. Okay. So we're going to talk more about different mediums in here. A medium is just kind of what sort of goop the light is traveling through. So the medium that light is traveling through in this room is just air. Okay, so air is a medium. And we have this phenomenon that can happen called internal reflection. And if you have two mediums, two medii, okay, if you have two mediums like this, okay, here we have of course, these young ladies are in the water. That's one medium. Above them is air. So that's the second medium. What can happen at the boundary of those two mediums is basically their image is hitting the boundary between the water and the air and being reflected back down. That's called internal reflection. Okay? So I think that's kind of cool.
Would you have to be in the water to see that?
You would have to be in the water to see that, I think. Yeah. Yeah. And Kay and I were talking about that this morning. She can actually relate to that, seeing the reflection. And here, when we talk about rainbows, we're actually going to see this right here is my liquid rain droplet. basically light comes in, okay, and it bounces off the back of the liquid water droplet and comes back out. Okay, now in between is something we call refraction. I'm coming up to that, but that's the internal reflection of a rain droplet to give you rainbows. So there's 2 R's you guys filled in. You filled in reflection and you filled in refraction. So refraction is also a player in creating some cool, what we call optical phenomenons, things that you see. So refraction occurs because refraction occurs because light is leaving one medium and going into another medium. These are 2 mediums, okay? Light is refracted. And it's refracted because it goes a different speed in these 2 mediums. And I hadn't thought about it much till kind of recently, but if I were to ask people what the speed of light is, they probably would ramble off 186,000 kilometers per second. That's the speed of light. But that's the speed of light in a vacuum. Okay, if you put light in air, it travels slower. If you put light in water, it travels even more slowly. If you put light in your diamond, it travels even more slowly. So as light changes these different mediums, okay, it travels at a different speed, and that has consequences. So refraction is because light is traveling at different speeds in these different mediums. So what light does is light is actually bent. Okay, and I'm going to kind of show you what I mean by bent. So light is traveling like this, it goes into another medium, and it's bent. Okay. So this example, you see the light coming at an angle. Okay. The light is going to go from air to water. Those are the 2 mediums, from air to water. And you can see the trajectory of the light. If it was going straight, it would go like this. Okay, but since it went a new medium, it goes like this. It veers, what we say, closer to the normal. Okay. Now, if light is going straight in, like what we say perpendicular to the surface, guess what? There's no refraction. It's a subtle thing. But here, we have light going along what we call the normal, and it's not refracted. If it's traveling at an angle, it's going to be bent. So that's a little bit of a player, not much, but in refraction. Okay, so refraction, it happens because light travels at different speeds in those 2 mediums, and it's bent, actually bent. All right, oops. All right, so hopefully this is not a real scenario that you'd be driving down the road and actually kind of doze off a little bit while you're driving. Okay, but you figure just say you're on a highway, okay, hopefully not going really fast, but you have gravel over here, and your car travels more slowly on gravel than it does on the highway, okay. So the thing is over here, and I kind of just put this over here. Over here on your right where the gravel is, okay, that tire is going to hit the gravel, and that tire is going to slow down. So basically, it's going to slow down, but your tire on the left is still on pavement. It's going to keep going fast. Okay, but eventually, both tires are going to leave the pavement and go into gravel. Hopefully, it's a bunch of gravel over there, no ditch. Okay, let's just say it was all gravel. So at some point, basically, you're going to be all in the new medium, and you're going to be just cruising along. That bending part was when you changed mediums. Okay, so that's kind of what refraction is. What's that? Oh. So here's a figure from your textbook kind of showing you, not anybody falling asleep at the wheel per se, but if you go from laminate to carpet, okay, you're going to be nice and smooth over here. We'll talk about frictional forces actually in chapter 6. Less friction. And here you're going to slow down, but this wheel slows down first. This one keeps going. That's why it kind of swings around. But now we've got the entire car on the carpet, and now it's just going to keep going straight. New medium. That's what light does. It's bent as it changes its speed. Okay, so refraction. This is still one more about just plain old refraction. So here is a pencil in water. Here's a pencil in water. You're like, how interesting. It's a very subtle thing, but if you look at the photograph at the top, I don't know if you can see the dotted line is basically kind of a straight line of the pencil. Now the pencil is in 2 mediums. Mediums? I guess 2 mediums. The pencil is in air and the pencil is in water, okay? But the light that's coming from the pencil that's in water has to be refracted. It's bent so we can see it. okay? So we see the pencil, part of the pencil that's in the air like normal, but the light is refracted back out to us to make the rest of the pencil that's in water, so it's bent. Okay. This is like if you've ever been like dangling your legs in the, you can kind of see it's like, really? Is that my leg? You know, it looks, it's bending. Light is refracted by changing when it goes through different mediums. Okay, so now on to kind of more a phenomenon with refraction. So, if you've ever wanted a little bit of extra more time in the day, like, oh man, if I could just have another 5 minutes in my day, everything would be fine. Well, actually, every day we get a little extra time in our day. And this is what's happening. Okay? So here we have the sun down here. Now, the thing about the sun and what's causing the refraction, I guess I should back up. I said the two mediums like air and water, right? Those are two obvious mediums. Clear back in Unit 1, you guys told me if you climb a mountain, the air gets thinner, okay? If you go back down to the sea level, the air is thicker. Those are different mediums. Light will travel at different speeds in thin air versus thick air. Okay, so that's actually what's causing the refraction here. So it's a kind of a subtle thing, but here we have the thin air, here we have the thick air, and here we actually have the bending of the sun's light. Okay, so the sun could be here, could basically be set, okay, and it's actually kind of bending up and over to us. The light is refracted. Now, where does it appear? Well, it kind of appears where the last known trajectory. This is us here. So what we see the sun is actually, like this thing says, like up here. So the sun actually looks like it's up here, even though it's really down there, because its light is being refracted when we see it up there. Kind of a little trick there. Okay, so that's refraction. That's refraction due to density. Refraction due to density. Now this is going to be, I'm going to talk about two mirages, and this is also refraction, but it's refraction due to temperature, air temperatures. Okay, so this happens, so if you've ever seen like a candle, like a lit flame, and you look behind the lit flame and you kind of see it kind of like dancing kind of behind the lit flame, okay, what's happening is that lit flame is warming the air around it, and so actually an object you see back there tends to kind of shimmer or kind of looks kind of almost like, and what's happening is you have chunks of air that are changing their temperature, hot, colder, hot, colder, hot, colder, and it's actually causing refraction of that light back there.
So that's what happens in a mirage.
Mm-hmm. Yep, that's what happens in a mirage. That's what also happens in astronomy. We talk about, have you ever seen like stars twinkle? Twinkle, twinkle, little star. Okay, the same thing. Basically, the light from the star is passing through the Earth's atmosphere, and the Earth's atmosphere has kind of an assortment of temperatures up there. So it kind of, that light is refracted too. That's why stars twinkle. Okay, so we're going to talk about two mirages. We're going to start with the inferior mirage. Now, we've all probably seen inferior mirages. Okay, both mirages have to do with temperature differences. And if you change your temperature of the air, basically you get a new medium, and if you have two different mediums, you can get refraction. So that's what's going on. So inferior mirages, I'm going to compare and contrast them to the other type of mirage. Inferior mirages are below. They're below the horizon, okay? And inferior mirages we've probably seen on a hot day, maybe when the pavement gets nice and toasty, okay? If you've seen something that looks like watery, that's an inferior mirage.
Those always trick.
What's that?
They always trick me. 'Cause
They
I
trick
think
you?
I'm gonna hit something. But
Yeah.
It's just a,
You cringe. You think there's something up the road and there's nothing.
Yeah.
Yeah, I agree. So this isn't that watery looking mirage, but this is actually showing you a mirage of a palm tree down underneath. Now, the dude would see two palm trees. He would see the normal palm tree, light coming to him from the palm tree, but he would also see an image of the palm tree like down below the horizon. It's an inferior mirage. Okay, and that's created by hot temperatures. Now, you've probably more likely seen this type of mirage, where, like Lily was saying, it looks like you're going to run into something. Okay, so this type of mirage is caused a similar way by just simply very hot temperatures. And so you can almost, this is a good example because you can see that white car here kind of reflected. It would be, well, the image twice, and the image would be upside down underneath the car. So the other type of mirage I want to talk about, that was an inferior. This is a superior mirage. Now, I've never seen a superior mirage, okay, but I have a photograph. I have a figure from your textbook, and I have a photograph. So a superior mirage, actually, comparing it to an inferior mirage, a superior mirage would actually be above the horizon instead of below the horizon. It isn't generally inverted, but according to your textbook, it would be right side up. So a superior mirage is created by the same or very similar phenomenon when we looked at freezing rain and sleet, the temperature inversion. That's what causes a superior mirage. Okay, again, I've never seen one of these, but the best I can do is to show you a figure from your textbook. So again, the refraction is being caused by chunks of air at different temperatures. Okay, and so you would see two boats, which would be a very scary thing. I have one more scary figure to show you. It has to do with rainbows. It's the scariest figure in your textbook. But this would be pretty scary too. Okay, so you see two boats. You'd see one kind of hovering, not inverted, and then one, the normal one. So this is a photo from the internet, and it's a mirage. Okay, it's a subtle thing. Hopefully you can kind of see the thing about this, and I tried to kind of find what I thought was a good one. Those are mountains in the distance that are actually, you see the mountains where they normally are, it's hard to tell, but also then kind of a version of the mountains hovering above. And that's created by a temperature inversion. But to me, they look inverted. They look like we took one of those Rorschach sort of things and the spot things like, what do you see in these spots? But I don't know. That is a superior mirage. Okay, so I said refraction was the bending of light. But another thing that refraction can do is also to separate light into its components. Kind of like diffraction separates light into its components. And actually, I believe interference can also separate light into its components. And the way this sort of refraction works, it works the same thing. You have two mediums, okay? But if you've ever played much with a prism, basically you've been dealing with two mediums, okay? You've been dealing with air in your chunk of glass. Now your chunk of glass is ground, so it's kind of got the dimensions going for it, you know, kind of how it's set up. But white light is bent, but the different colors are bent differently. Like this slide says, actually red is bent the least and violet is bent the most. So that's where you have kind of a fanning out of the colors. Okay, so this is refraction also, but it's bending, the components are separated out because they are refracted different amounts. This is refraction. All right. So, related to refraction, related to kind of this idea that the shorter wavelengths are bent the most and the red color is bent the least, okay? We have this idea of a green flash. Now, where it says setting sun, if you want to, and I did double check this, if you want to put setting and rising sun, you can. Because it happens both as the sun is rising and the sun is setting. I've never seen a green flash either. I think I might have. I don't know.
Yeah.
Have you?
Several.
Oh, I'm jealous. Kay's seen green flashes before. But what happens is basically, oops, come back. What happens is did it kind of look like this? Or, I don't know. You watch the sunset and it's beautiful. It's orange, yellow. Be careful of your eyes, okay? But as the last tip of it sets, actually, it's no longer that color. It's green. So.
The ones I have seen have been more spread out.
More spread out? Okay, very good. And was it Like, what was your horizon like? Was it the desert, or was it,
No, in San Diego on the beach,
okay, the ocean? Oh,
over the ocean.
okay, let's
And I
go.
gave that up to move to
I
Iowa.
know, what are you thinking?
What in the world?
Don't think about it too much.
Like earthquakes in the Mirages.
Yeah, that's true. No more earthquakes.
Had several of those when I lived there.
Something.
Got thrown out of bed once by one.
Oh, really?
I've had to
So-
settle those
Oh,
more than 20.
that's gotta be nice to wake up to.
But the reason it doesn't appear as blue, indigo, or violet is because those are actually scattered by the Earth's atmosphere. So that's why kind of next shortest on the length is green. So Roy G. Biv. So, okay. Rainbows. Okay. So if I ask you somewhere on the test about a rainbow, hopefully you can tell me their criteria to see a rainbow. One is that the sun needs to be low on the horizon. That's criteria number one. It could be sunrise or sunset. Criteria number two is that you need to have some sort of liquid water droplets. Okay, liquid water droplets, i.e. precipitation, basically kind of some leftover precipitation. But it needs to be the opposite horizon of the sun. So if the sun is rising in the east, then your precipitation needs to be in the west. Okay, if the sun is setting in the west kind of low, then your precipitation needs to be in the east, that sort of thing. So they need to be opposite horizons. Okay, and then basically, it needs to be clear between the two, the leftover precipitation and the sun. Okay, because you need the sunlight to get to your suspended liquid water droplets. I guess that's it. 3 criteria. So in order to see the sun, you are going to put yourself, let's see, you are going to have in order to see the rainbow, in order to see the rainbow, you're going to put the sun at your back. So it looks like this. So here is the setting or the rising sun, kind of low on the horizon. Okay, here is your leftover kind of precipitation. And then here, this little stick person is you. And you are going to look this way and hopefully see your rainbow with a pot of gold at the other side. So that's kind of how that works. Goodness. Okay, so you may have already know this, but there's possibility of seeing 2 rainbows. The secondary rainbow, if there is one, will be outside of the primary rainbow. And there is a deal with regard to the order of the colors. So the reds kind of overlap. So from inner to outer. So the violets overlap? Oh, no, the reds overlap. So the primary rainbow looks like this. It'll be inner, and it will go Roy G. Biv. Okay, and then the secondary one, if there is one, will go Roy G. Biv. This is the secondary one. This is the primary one. Okay. So the physics of a rainbow. What happens is that both of the R's we talked about happen. So we have refraction, then reflection, and then refraction again. So it's kind of sandwiched. Refraction, refraction, refraction. So basically, you're going to see the scary figure coming up here in a minute, but basically light enters the rain droplet, and what does it do? It's changing medium from air into liquid. And so light is going to be refracted, it's going to be broken out into its components. And then it's going to reflect off of the back of the water droplet, internal reflection. And then as it exits, it's going to be refracted one more time. R. Okay, so here we have the sun must be over here, low on the horizon. Sunlight is coming, interacting with those liquid water droplets, and she is seeing a primary rainbow. This was the scary figure I was talking about. So like not drawn to scale. That blue thing is a water droplet. I just think that is so funny. The blue thing's a water droplet. So you see the sunlight coming in. It's broken out into its components, refracted just like a prism up here. Broken out into its components, and then we have internal reflection back there, kind of like we saw those young ladies in the swimming pool, because it's the boundary of the liquid and the air. So it reflects, and then it's refracted one more time, okay, to come separated down here. I think that's cool. So if there is a secondary rainbow, this is what it looks like. Okay, basically we have it coming in at a different angle. Again, we have refraction. We have two internal reflections, reflection, and then we have, it's going to be refracted one more time as it exits. So over there on the left is a photograph. That's kind of why I dimmed the lights this morning. There's the secondary rainbow right there.
Has there ever been like a triple rainbow?
Not that I know of.
I've seen a double rainbow, but nothing.
Triple
bigger.
rainbow?
They're common.
I have to Google.
What? I didn't.
I'll do it right.
Okay. Well, keep up though, because we're going to finish the chapter here. So rainbows are one optical phenomenon. Another optical phenomenon are halos. Halos, bless you. Halos are kind of like an angel halo. And halos can occur, I have some photographs to show you, but they can occur around the sun and around the moon. And the thing that creates halos are ice crystals. So one of the things we talked about, and they had to be kind of wispy clouds, wispy high-level clouds, and that probably leads you to think cirrus clouds, okay? Or cirrostratus. So those are the little ice crystals that are creating these halos. And here are images of halos, photographs of halos. This is a halo around the sun, and this is a halo around the moon. Yeah, you can just kind of barely see this.
It's just light reflected.
It's just what?
It's just reflected light.
It's refracted, actually. Yep, refracted, yep. Light is being refracted from either the sun or the moon. Yep.
My dad always said that meant it was going to rain, so now I can tell him that it's
Well, yeah,
it
yeah.
is.
There is, and tell him it's refraction and tell him that he's kind of right, possibly. Because if we start with those cirrostratus or cirrus clouds, actually that can be a precursor to the other clouds that bring us precipitation. So, yep. Halos can actually kind of foretell precipitation. So those were halos, and now onto sundogs. So they are related they are both caused by ice crystals. So again, you're going to have cirrus or cirrostratus clouds, so ice crystals. Now the thing about sundogs, though, unlike halos, is sundogs only occur when the sun is relatively low on the horizon. So I know sometimes here in the mornings on my drive, I'll look up and I'll see the disk of the sun, and then you can have a pair of them. You can have sundog, kind of on either side of the sun. So yeah, they're cool.
Tricky.
They are. What's that?
It's tricky.
Tricky. But sometimes they'll kind of look like a little mini rainbow too. So it's not the best picture of a pair of sundogs, but not bad. This little blob here in the middle is the sun, and then we have a sundog on either side. So.
Why are they called sundogs?
I don't know.
Never discovered his name in
Yeah. They're also called Parhelia, which I prefer sundogs, but. Yeah. Another thing is the sun pillar, and sun pillars are also caused by ice crystals. And the word pillar kind of gives it away. It is like a pillar of a shaft of light basically coming from the sun. Again, the sun needs to be low on the horizon, and it will extend either, vertically up or vertically down. And here's a picture of that. That is pretty. Road trip. No. So, just a couple other, two more phenomenon, I think. But we're switching gears from ice crystals, ice particles now to liquid particles, back to liquid particles. Okay? So we have these thing called glory. I've not seen one of these either. But you don't have to be in a plane to see one, but sometimes you can actually see it. Now what's causing this is kind of what, a little bit the refraction process that happens in a rainbow. These are liquid water droplets in the cloud there. So it must be kind of a warmer cloud. And this actually is a glory created by fog. Or by smoke. Yeah. So those are glory. And then last but not least, we have corona. So corona, like glory, are created by liquid water droplets. Okay? And corona, like halos, can be around the sun or the moon. So corona. Bless you. But you can tell the difference between a halo and a corona in, like I said in the slide, that these would be kind of, and they can have some color to them too, but they touch, unlike a halo, they actually touch the disk of the sun or the moon. And since these would be liquid water droplets, you're probably looking at maybe a middle level cloud like the alto stratus. Okay. Yeah. See, to me that almost looks like I know I got this figure from your textbook. To me that almost looks like a halo again.
Yeah.
Yeah. That's what your author, I have to double check, but that's what I got him down for as a halo. And this is not the best picture either, not a halo, a corona, I'm sorry. I have him down as this is a corona, and this is not the best picture of a corona around the moon either, I think. So,
Is that like the ring around the moon?
yeah.
Or is that also a halo?
Well, it depends on if there's space. If it's touching the moon like this is kind of implying, then this would be a corona. If there's space between the ring, then it's a halo. And that's why, to me, this is a corona. But,
See, if it's like, sometimes when you see the moon, it's called a blood moon because there's that red around it, or there's the yellow around it.
yeah, that probably is like when the moon's kind of low on the horizon, maybe, kind of.
No, it was high in the sky.
I don't know. But that may, it
But
could be,
there
it
was, like,
could be
no
kind of the
space
color.
in between the
Okay,
things.
yeah, that could be caused by like altostratus clouds. Yep. Okay, so the last one, last but not least, these are the optical phenomenon, some of them that we've talked about in this chapter or even outside of this chapter. The last column is what particle is causing the optical phenomenon to occur. Okay, and then the first column is what do you call that? What do you call that physical phenomenon that's happening between the particle and the light? But on my review sheet, I think I say how did they occur. This is kind of the information I'm asking. You know, what causes rainbows, rain droplets? Okay, what causes sun pillars, ice crystals? Okay, what causes sundogs, ice crystals? So you don't worry too much for your test anyway about that first column. Okay. Very good. Okay, if you have any questions between now and Friday, let me know.
Gotcha. 3 rainbows.